Welcome to the continuation of differential calculus. In this video, we are looking at higher order derivatives. With higher order derivative, we want to look at what happens if you differentiate a function and you are asked to differentiate again and again and again. And so here we want to look at how we can take the first derivative, second derivative, third derivative, and so on and so forth. If you are given a function, let's say f of x, to be equals to, let's say we have 2x to the power 4. Now, when you take the first derivative of the f of x, the notation is written as f prime of x. In that case, your first derivative of this would be 8x to the power 3. Then when you differentiate again, the notation will be f double prime of x. Again, we'll give you f triple prime of x. When you go further, instead of going to IV, you can write as 4 of x. Then the fifth one can be written as 5 of x. And this can continue on and on and on until we have f of n. And so we can have the first derivative, the second derivative, and so on. And so if this is the original function, this is the first derivative, second derivative, third, fourth, fifth, and so on and so forth. If the function is given in terms of y is equals to the function, now what happens if you differentiate the y? You know you are going to have y dy dx. And I want to differentiate again this same function. We want to differentiate it with respect to x. And so that will give us, it means I'm going to have two of the d's. So we have d squared and then y. Then we have, remember this is with respect to x. So we're going to have dx and then ds being multiplied. And that will give us dx squared. Maybe you can say that then why not make it x squared like this? Actually, writing dx squared like this is the same as writing dx squared in terms of calculus. Now, if I want to further differentiate this one again, then I want to take the third derivative with respect to x of the square y dx squared. Then again, when I differentiate the second derivative with respect to s, then I'm going to have d, that's d times d here will give me d cubed, then divided by ds cubed. And so this can continue until if I differentiate to the nth term, I have dny, then dx n. And that's the notation we normally use for order of derivatives. So you have the first order derivative, the second order, third, fourth, and so on and so forth. So we'll take examples and see how it works for higher order derivatives. So example number 1, we want to have this particular function y is equals to x to the power 6 plus 2x cubed minus 3x squared plus 4x plus 1. And we have to find the third derivative, that is the cube y over ds cubed. And that is the third order derivative. So we want to differentiate 3 times to get what we want. And so if I take the first derivative of this function, then I have dy dx is equals to 6x to the power 5 plus 6x again to the power 2. That's for the second part. Then for this, we are going to have minus 6 again x. Then this alone will give me plus 4, then plus 0. So this is the first derivative. They want to say the second derivative. We want to take the second derivative of, with respect to x, of dy dx. Okay, and second derivative, that it means we are going to take the into bracket of 6x to the power 5 plus the second derivative of, with respect to x, 6x to the power 2 minus the into bracket 6x, then plus the derivative with respect to x of 4. Actually, you can avoid this particular step, but I just want you to understand that that is how we take the second derivative of the function given. So when I differentiate second one, I'm going to get the square y dx squared equals, here is power 5, because we had it as 5. Then 5 times 6 is 30, x to the power 4 plus 12, the second one, x, then minus 6, then plus 0. So that's the second derivative. Right. So the third derivative, that means when I differentiate this one, I'm going to have the cube y ds cube, then 4 times 30 will give me 120, x to the power 3 plus 12. And this will be 0, this will be 0, so this will be the answer. So if you take the third derivative of the function given, this should be your result. Example number 2. This is a very easy question. You can pause the video and try your hand on it. Given that the function y equals this, now say find the square y dx squared and state the set of values of x for which this is equals to 0. And so when you find the differential, the first and the second derivative, then you find the zeros of the function that you get. So for this, we will say first derivative dy dx will be equal to 4x to the power 3 less 3x to the power 2 plus 4. And remember that minus 1, if you differentiate, you get 0, so that wouldn't come at all. Then we can take the second derivative, the square y dx squared, 12x squared minus 6x. Right. And find the values of x for which the function is 0. I mean, the function is 0 means that we are saying the square y dx squared is equal to 0, which means that 12x squared less 6x should be equal to 0. Then we find the values of x. So to find the values of x, we can easily do the factorization here by factorizing 6x out. Then we have 2x minus 1 equals 0. Right. Yeah, that is correct. So this is equals this times this is equal to 0 means that either this is 0 or that is 0. And so we can say 6x equals 0 or 2x less 1 equals 0. So if it is 6x that is equal to 0, then our x will be equal to 0. Or if this is equal to 0, then we can say 2x equals 1 and then x is equals to half. And so the values of x for which the square y dx squared will be that the values of x will be x equals 0 or x is equals to half. Now let's look at example number 3. For example number 3, this question seems to be different from the first two examples that we've solved. This has to do with implicit function like we did earlier video before this video. If you've not watched that, you need to go back and watch that before you come back to this. Now this is explicit function and we have to show that this is equal to that. And you can see the arrangement of this means this is explicit. It means it was differentiated twice in implicit form. Sorry for that. But the equation itself is explicit. So we have to convert this one to make it implicit so that it will match the solution that we want to calculate for. So what we do here is to rewrite the original equation y into bracket x squared plus 5 is equals to x. In this case, this now becomes implicit function, right? So we can differentiate using the product rule. We hold this, we differentiate this, then later we hold this and differentiate that. And so when I hold y and I differentiate this, I will have 2x as that. Then plus, remember that this hasn't got chain rule, and so plus straight away we hold x squared plus 5 and differentiate y, and that will be dy dx, which is equals to 1, because when we differentiate s you get 1. So we can rearrange this one as 2xy plus x squared plus 5 dy dx equals 1. Now we are going to take the second derivative of it, and remember that this now becomes a product rule having 2s and y. It means I can hold 2s and differentiate y, which will be dy dx, plus I'll hold 2y and differentiate x, which will be just 1, so I can choose not to bring the 1. Then plus here the same thing, I'll hold x squared plus 5 and differentiate this alone, and that will be the square y dx squared, plus now hold dy dx and differentiate dy dx and differentiate this alone, which will give me 2x. Everything is equals to the differential of 1 will be 0. So now rearranging this, I'm going to have x2 plus 5 d square y dx squared, that is for this part. Then note that this and this have like terms, so I can say plus 2s plus 2x, then dy dx. I hope you understand what is done, what I've done over here. If I factor this and this out, then I'm going to have this plus this to give me this, to give me what I have here, and then plus 2y, that is this part of it. Everything is equal to 0. And finally, I can write my answer as x squared plus 5 d square y dx squared, plus this will be 4x, they are like terms, then dy dx plus 2y equals 0. And so that is what we have to prove our answer to be, and that is the final answer. And this is exactly what the question gave us. You see this answer, you can see the same thing we have here. Okay, so that's beautiful. Okay, now let's look at example number 4. You can pause this video, simplify it yourself or solve it yourself, and then you check your answer. Right, I believe this is what you did. Now we want to find the fourth derivative of this function, and so we can write this function as y. This is not implicit, so you can keep it as explicit, is equals to 6x to the power negative 4, and that will be very easy to handle if you go by this means. Then you take your first derivative, so let me move this way. First derivative will be dy dx. Now 4 times this is negative 24x. Remember that I'm subtracting 1, so that will be negative 5 from this. Then the second derivative will be 5 times the 24 will be 1 20 positive. X to the power minus 1 again will give us 6. And then we go for the third derivative. Third derivative would be the cube y ds cube, and we are going to multiply 6 times 120, and that will be negative. Remember that we have negative, so 6 times 120 is 720. X to the power negative 7, because it will still be minus 1 again. And then finally we want to take the fourth power, which will be the 4y ds 4, and here the negative times negative will be positive, and we are dealing with 7 times 720. I'm sure that will give me positive, so 50, 40, x to the power negative 8. So this will be the answer for that. I believe you had it correct. Now let's take this question as the final question for higher order derivative. Here we have to determine y prime 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 if the first one has been given second, third. The first you can do, the second I've done similar one, you can do it, but I want to do the third one so that you try the first two on your own. Now the third one, we want to find the third derivative of this, and they say a, b, and c are constant. So if I differentiate y, which I have, sorry for that, dy dx, so I'm going to have 3a x to the power 2 plus b, just that when I differentiate bs, I'll get just b, and plus c will be 0. Remember, they are all constant. And so I go for the third derivative, or I can even choose not to use the symbol here because the question says I should use y prime prime, so I can call this double prime. Then when I go for the third prime, oh sorry, this is the first prime, so I'm now going for the double prime. So again, I have 2 times this will give me 6a x plus 0, because b is a constant, so it will be 0. Then I go for the final one, prime, and that will give me 6a. So that is the answer. So triple prime, or third derivative of the function, is going to be this. Now for the first two questions, I believe you can do it. If you want a clue, you can just differentiate this, and then you go step by step like I've done. And for the second one, just turn it as that, and then when you differentiate minus 1, you keep differentiating and you get your answer. So we want to have this video as the video number 5 of this series, and you watch for the last video of the differential before you go for the application of differentiation.